Okay, 4:30. I wanted to do an example, since we didn't get to it in class, of how to determine dynamic scope. So specifically what we're going to do is we're going to look just at this variable z and figure out what its value is and where that name z is bound when the program is run. So the question is, does this z refer to int z that is local to main and declared there, or does it refer to int z in h and declared there when dynamic scoping rules are the rules that are in play? And I think the first thing to do with both the static and the dynamic scoping, I did this in class, but I want to make it real explicit. Draw your scopes. And what that really means is draw your blocks graphically by looking at where each block starts. So like void main starts a new block because we have a new curly brackets, and draw a line that includes the entire block. So you have a nice graphical depiction of where that block starts and ends. Similarly, we can do void G and void F and void H. And so now you can really see the structure of this program. So if we were doing static scoping rules, it's really easy to figure out where this z is going to be bound, because what we do is we check our most local scope, and we say, is there an int z declared here? There's not. And so it's not bound to anything in F. And so what we have to do is go to the parent. So you basically are going outside the onion layers here that we've got to figure out where that z is. So we come out to the parent and we say, all right, in the parent, do I have an int z that's declared up above? And the answer is no. So there's no z up here. So I go one more level out. And now I say, all right, at this point, if I'm at this point in the program, is there a z visible from here locally? And there is. It's this int z. So that's how we did the static scoping rules in class. But now we want to look at how to do dynamic. And to do the dynamic scoping rules, really what we need to do is run the program by hand, which means that we're going to have to keep track of the call stack. All right, so let's keep track of the call stack and see how this works. So obviously main, and this is a C-like language, is the first call that's made. So there's a call to main, and you'll find it helpful to do the following. Use square brackets and put any variables read through the code as it's running, and use square brackets to store the variables. So notice main, what does it do? It declares a z and sets it equal to 12. So main now has a local variable named z, and it's set equal to 12. This is just a definition, so we can ignore the definition and jump down to the next line of executable code. This is a bit of executable code. What it says is call this method that I just defined G. So what that does, remember, is pushes G onto the stack. And so now we've pushed G onto the stack by calling it, and we've jumped to the start of G. All right. And notice what G does. G declares two variables immediately. So it declares an x, which is set equal to 3, and it declares a y, which is set equal to 4. And then it has a definition for f, and it has a definition for h. Neither of those are executable, right? It's not being executed, it's just a definition. And so the very next thing that we do is we run h. And so we push h onto the call stack, and notice my stack is growing down, which is different than a lot of times when we draw stacks. But we push h onto the call stack, and so let's give it a spot for its variables. And we jump up to the definition of h and start running it. So here at h, we see that we declare two variables, z and y. So let's declare those, and those are locally declared. So there's z is equal to 3, y is equal to 2. And then we call f. And so we're going to do this again. We're going to push f onto the stack, jump to the definition of f, and notice I've got area for f's declared variables, but nothing in this example declares a new variable. So now we get to this line of code that we're interested in. We're going to set z equal to the sum of x and y. And the question is, what does z refer to, what does x refer to, and what does y refer to? Because we have two y's in this code, we have two z's in this code, and we have one x. So that x is pretty obvious. But let's look at how you do that. In dynamic scoping rules, what you do is you look by starting where you are in the stack, the very bottom of the stack, and you keep searching up the stack until you find the variable you're looking for. So we're at F, we want to figure out which Z we're going to use. There's no Z locally to F. So then we have to jump one hop up to H and ask the question, is there a Z local to H? And the answer is yes, there's my Z local to H. And so this Z is really this one that's stored at H, which is this one we declared here. All right, so this is the value that we're going to be replacing. And now we got to figure out what X and Y are. So let's look again. There's no X or Y declared at F. There is a Y declared at H. So this Y is going to be the Y stored locally at H. But there's no X, so we have to keep looking. And the X is the X stored at G. So now we know what's going to happen. We're going to take X, which is 3, Y, which is 2, add them together, which is 5, and replace the Z stored at H with 5. So really what we did is we said the Z at H is now 5. That is what we have done. Okay. But now let me show you why this is called dynamic, because this completely depends on the actual call stack, not the structure of the code. So for instance, instead of putting H here, I won't change any of the structure of the code at all. Let's look at what happens if I call F directly. And now I need a new stack because this is going to be a different run of the program. So again, I push main on and I create my variable Z and set it equal to 12. Then the next thing I do is call G. So I push G onto the stack and I create X equal to 3 and Y equal to 4. And the next thing that I do is call F, which means that I push F onto the stack. And now I'm sitting here at void F, and I'm asking the question, what does Z mean, what does X mean, and what does Y mean? And notice this time the answer is going to be different, because when I go looking for Z, I'm going to look starting here in the call stack and jump up and say, well, first I'm going to check F. Is there a Z here? No. So I need to jump up my stack. I'm going to go up to the parent in the stack, which is G called F, and say, is there a Z here? No. And so then I'm going to jump up again to main, and I'm going to say, is there a Z here? And this time I found Z, and notice it's not the same Z I found before. So the fact that I called a different function without changing any of the structure of the code, I've changed which Z I'm referring to. Before I was referring to H's Z because H called F, and so when F looked for Z, that was the most recent Z. But this time the most recent Z is actually main's Z. And so this time when I assign the variable, it's going to be here. Similarly, when I looked for X and Y, before I found H's Y and G's X. This time there is no Y here, and so when I jump up the stack, what I'm going to see is an X defined in G and a Y defined in G, and so that is what I'm going to add together. So I add 3 plus 4, which is 7, and I replace Z's value in main with 7. And so here you can really see the difference between when you're running dynamic. What's kind of difficult about dynamic scoping is you can't just look at the code. You have to know the actual run of the program, and you can't even know this necessarily as a programmer, because what if this is an if statement? If some user input run H, say, else run F. Notice that depending on the user input here, I might do my first example and then my call stack would look like this, or if the user input is different, I would run my second example and look like this. So the way the variables are bound has to be determined not at compile time but at runtime, because we have to know the actual path that the input forced us to take through our program.